All right, so in the forum, there were requests for 3 questions, all from section 13.6, homework 20, problems 2, 4, and 5. So I'm just going to go in order of them through the set. I've already pulled up problem 2 right here, where we're instructed to find the circulation for f dot dr, where v is given by this vector field, and C is a triangle with those vertices, assuming counterclockwise orientation is viewed from above. So, thinking about this in the context of at some point you're going to have problems and not know what homework section they came from. You won't know section 13.6 was the Stokes theorem section, so you must use Stokes theorem. Let's just think through how we know the right way to solve this problem. So we're asked to evaluate a line integral. So we learn first how to directly evaluate line integrals with parameterization. And then the other way we've learned to deal with line integrals is with the fundamental theorem. If we find a potential function, or Stokes/Green's, if we couldn't find a potential function, then del cross f would be non-zero and we could evaluate it that way. Oops, wrong thing. So if we check out this vector field and curve, this is a closed curve, and if I sketched it, here's my z, my x, and my y. It goes between 0, 0, 0, 1, 0, 0, and 0, 1, 0. So it's this triangle shape right here. And that's a closed curve, so I know Stokes or Green's is allowed. And it's not given to me in terms of a parameterization, so that seems like it would be difficult. And if I wanted to try and integrate this function, maybe I could apply the fundamental theorem. But just looking at it, I sort of know if I integrate this x plus y with respect to z, I'll get an xz, but there's no z here, so it must be that eventually that process would break down. So I want to use Stokes' theorem to solve this problem, which means I'm going to use this formula right here. And so all that I have to do is take that curl and then define the surface that I'm integrating over. So let's do the easy part first. I know I want to use Stokes. I know I'm going to have to take this curl. So even if I get the region wrong or can't figure out what the region is supposed to be, at least I could show my work for this part. If you prefer to use the formula, that's fine, but I always do it the determinant way because that's a little easier for me. And the f in Stokes' theorem is the f that was inside the request for the line integral. So for this problem, that's v, which was given by this equation right here, y I hat, x squared plus y squared j hat, and x plus y k hat. And so I'm just going to evaluate this line integral, or sorry, this curve. So for I hat, I'm going to get d dy of x plus y minus d dz of x squared plus y squared. And then the j hat, I always have that extra minus sign. And then I'm going to get d dx of x plus y minus d dz of y. And then k hat, we're back to addition again. No extra minus sign. And I'm going to have d dx of x squared plus y squared minus d dy of y. And I just have to take those partials and simplify everything. So the derivative with respect to y of x plus y is 1. And the derivative with respect to z of x squared plus y squared is 0. The derivative of x plus y with respect to x is also 1. And then the derivative with respect to z of y right here is going to be 0. And then derivative with respect to x of x squared plus y squared is going to give me 2x. And derivative with respect to y of y is 1. So my del cross f is just going to be 1 minus 1, 2x minus 1. And I'm going to plug that in right here and turn it into a surface integral. And in order to do that, I need to know a normal vector. So I have to check back to the way that I was told this problem is oriented. I'm told that this is a counterclockwise orientation as viewed from above. So if I'm up here looking down at the coordinate plane, I see counterclockwise like that. So that's going to be going this direction. Or if you think about it, the whole thing lives in the xy coordinate plane, and so we can just see counterclockwise right there would be going that way. What's important about that is by the right-hand rule, I know that that surface is oriented with that normal vector. And instead of having to calculate my normal vector from an equation, I can just look at this and see that the thing that's perpendicular to the xy plane is going to be 0, 0, 1. I basically drew the normal vector just now. It has to be right there perpendicular to the surface, and the thing that's perpendicular to x and y is z. Oh, actually, I do need to leave that there. Well, no, it's confusing. Okay, so this v dot dr that I was asked to solve is going to be a double integral of 1 minus 1, 2x minus 1, dotted with 0, 0, 1. And usually we have ds right there, but that's because sometimes we have to convert curved surfaces into the 2D dA that we're used to. In this case, the surface is already a flat object. Its ds is dx dy because it's a flat object that lives in xy. So there's nothing fancy to do there. If you didn't have that occur to you, you could remember that this surface is some segment of z equals 0, and you could actually directly calculate the normal vector in dA the usual way. You would just get 0 for all the partial derivatives. So now I just have to go ahead and set up the bounds of integration to finish up my problem. So that's going to be easier for me looking at that image. Where I remember that those points where it intersects are at 1. So at a glance, I can tell that this upper line right there is y equal 1 minus x, because I have intercept 1, and then I just go down 1 over 1. So negative 1 is my slope. So if I'm trying to integrate this area, I go up to y equal 1 minus x, and I'm bounded below by 0. And then I can just look at this shape, and I can see that x is bound from 0 up to 1 along the x-axis. If I wasn't sure about that, I could do that thing where I set my two bounds equal and end up solving for x equals 1. But once I decide on those bounds, the order I want to use is dy dx, because I wrote y in terms of x. And so that's the integral I'm looking to solve. And then this dot product is going to give me 0 times 1 is 0, 0 times minus 1 is 0, and 1 times 2x minus 1 is 2x minus 1, dy dx. And from this point, you would just go ahead and evaluate it, which is a, I guess at this point, chapter 12 kind of problem for you. But you will get some number and put that answer into WebWork. I'm not going to do that just for time, because I think that we've practiced that a lot up to this point. So, are there any questions about that problem? David, I don't think that's the one that you requested. Sorry. Okay, cool. And then the other two problems were 4 and 5, so we'll go ahead and move on to those next. So problem 4, we're told use Stokes' theorem, so we don't have to do all that thinking about what's the best approach here. And we're asked to change this integral to an equivalent surface integral and evaluate it. We're given this f and that shape. So I only did one example like this in the lecture videos. Like I did a lot of practice with Stokes and only one with using Stokes to swap integrals. So if you wanted to go back and check that example, I think I called the video converting example. And it's the less common thing we do in this section, so that's why there's only one. The idea is that we have this paraboloid, they've told us, starts up here at 4 and then goes down to the xy plane. That's our surface and it's oriented upwards. And we are supposed to evaluate the surface integral over this surface. And you can kind of imagine that if we start to set up this surface integral, because we've got these x squared and y squared in our equation for z, our normal vector is going to be complicated. Z takes on different values across the entire surface, so if I need to plug in that z, it's going to be a whole mess. And my ds will be complicated as well. So what they're recommending is to use Stokes' theorem to change this to an equivalent but easier integral to solve. So using Stokes' theorem directly would be to say this surface is bound by this curve down here, so I can convert to a line integral. But we can take it one step further and say that curve, line integral across it, is going to be equivalent to any other surface with that boundary. So we can go ahead and use this surface instead. It has the same boundary as the surface that we started with, but it's easier. Z is 0 everywhere on that surface, and the normal vector is easy, it's k hat, like in the previous example. So kind of the reasoning here is I could have converted my first surface, S1, into this line integral. That's this first step. But also I could convert this line integral into this new surface, S2. That's the second step. And so I can just skip the line integral in the middle and go ahead and do the surface integral, which you wouldn't have intuition for on your own maybe, but this is going to be easier than doing the first surface or the line integral, and that's why WebWork told you to do it this way. So no matter what, we're going to have to take that curl, so let's go ahead and do that first. Oops, I need my ddx, ddy, and ddz. And then it's xy squared xyz. So I'm going to have I hat times ddy of xyz minus ddz of y squared. That's going to give me, well, I'll write it out fully. And then simplify in the next step. Then j hat of ddx xyz minus ddz of x. Plus k hat of ddx y squared minus ddy x. And then when I simplify all this, I'm going to get xz minus 0 minus j hat of yz minus 0 plus k hat of 0 minus 0. So it's xz, yz, and 0. I went through that a little bit more quickly because I went through the curl on the first problem a bit more slowly. So if that is rusty for you, go ahead and check that first example. So that's my curl, and then I also need to know a normal vector to use this Stokes theorem. And I'm thinking about the second surface that I highlighted in yellow up here. And like in the first example, we can actually pick this surface, the normal vector, sort of by looking at it. We know that it's going to be that 0, 0, 1 because it's a flat object in the xy plane, oriented upwards. If it was oriented the opposite direction, we might have a minus k hat component instead. And if you didn't remember that way to do it, then you would just ask yourself, what is z on that surface, and then plug into the formula. But z is 0 here, so it's simpler. And then at this point, you would go ahead and start to set up your double integral for the second surface. But I want you to note that del cross f dot n is going to give us 0. We've got xz times 0 plus yz times 0. So those two terms go to 0 because of the zeros in the normal vector. And then the last term is 0 in del cross f dotted with 1, so that gives us 0 again. So no matter what the bounds are, we're setting up a double integral of 0 over the area, which is going to be 0. So you don't have to set that up. It would be unnecessary to do that. In fact, calculating these components of the curl even wasn't necessary. If you had looked at this and said, my n is going to be 0, 0, 1 to start, then you would know I only need the k component of the curl. You could have checked that instead of doing the first two, and then gotten to this point of realizing the dot product is going to be 0, so this integral is 0. And that would be enough work on an exam. And it's certainly enough work to finish the web work. If we were going to finish this problem, like if we had gotten something that wasn't 0 inside, we would just need to go back to the definition of the surface. Remember, it's happening when that 4 minus x squared minus y squared from the first surface hits the xy plane, where z equals 0. So that's just going to be a circle with radius 2. the way we would have set this up would be to say we go from 0 to 2 pi, we go from 0 to 2, the thing that's inside r d theta. But again, you don't need to do that because we have a 0, so we know that this integral will be 0. Same as with 1D integrals. Are there any questions about that one? All right. And then the last request was to look at problem 5, which asks us to find the work done by the force field F as an object moves counterclockwise around that circle. So to start this one first, you need to know or remember from when we first learned line integrals that when you're asked to do work, that's them asking you to set up a line integral problem. So we're trying to evaluate f dot dr for f given by this around the curve C that is a special circle. I should do it like this. So the way that this circle is written, the x is offset by 2, so instead of the center being at the origin, it's over here at 2, 0. And then it has radius 1, so it's going to go to 1 and 3. It's going to be that circle right there. And we're told that it's oriented counterclockwise, so that's going to be this direction. Make my arrow a little better. Like that. And when we're given the description of this curve, that's C, it's sort of already a hint that you're not going to be parameterizing it because they don't even tell you where it starts and where it ends. It's just this circle. They're saying you could pick any point to start from and end from on the circle. It's going to be the same thing. So if you wanted to parameterize it, you would have to define for yourself like, oh, I start at this point and then end at the next point. Like once you reach it going all the way around. So our first way of doing line integrals where we parameterized has extra steps to start it here. That's not great. So that leaves us with either the fundamental theorem or Stokes/Green's. And the fundamental theorem, we would need to find a potential function for this capital F. It has one component, j hat, so we wouldn't have a whole lot to integrate. But if I integrated this with respect to y, I would get xy out of it, which means that when I take the derivative of it, I should have a component y in the I hat component. But since I don't have that, I know that this isn't going to have a potential function. So if I saw this problem out of context, that's how I would know I can't do the fundamental theorem to this problem. And that leaves me with Stokes as the easiest way to do it. And I sure hope that when I take the curl dotted with the normal vector, I get a constant problem, so I don't have to worry about the funky shape of this circle. But that's a later problem. I know now that I want to do Stokes' theorem, so I'm going to go ahead and take that curl. Because even if I can't figure out my surface or my normal vector, because it takes visualizing and remembering what function shapes have, I can definitely compute a curl for partial credit on an exam. So my f is pretty easy. It's got a 0 in the I hat, a 0 in the k hat, and it's x plus 2y squared in the j hat. So from I hat, I'm going to get d dy of 0 minus d dz of x plus y squared, x plus 2y squared, minus d dz of x plus 2y squared. Maybe you've already seen that that's going to give us a 0, but I'm going to write it all out just to be safe. For j hat, we're going to get d dx of 0 minus d dz of 0. So that one's not a whole lot to write out. And then k hat is where stuff happens. We've got d dx of x plus 2y squared minus d dy of 0. And when I simplify all this, in my I hat, I'm going to get 0 minus 0. In my j hat, I'm going to get an even easier 0 minus 0. And then in my k hat, I'm going to get 1 from that first derivative minus 0 from that second derivative. So my del cross f here is 0, 0, 1. Next up, to set this surface integral up, I'm going to need to know the normal vector for the surface. So if I could see you, I would be making that curl hand gesture, but you wrap your hand around this curve and you know that the normal vector must be coming out of the page by the right hand rule. So like all of the other problems we did in this video, I guess, the normal vector is 0, 0, 1. Because the object lives in the xy plane and it's oriented counterclockwise, or when I wrap my fingers around it, my thumb points out the page. So that's the normal vector. So I'm going to have to set up a double integral of del cross f dotted with n ds. But my del cross f dot n is going to be 0, 0, 1 dotted with 0, 0, 1. So that's just going to be 1. And then since this surface doesn't have curves to it, ds is directly dA. This is again that case where I'm on z equals 0, that's a flat object, so if I tried to plug it into that formula for converting ds, I would just get 1 out of it. So this is just a double integral over the surface that I just shaded in. And from when we learned about double and triple integrals the first time, I hope you remember that double integral means area. So I don't need to set up the bounds for this object, I just need to say what its area is. It's a circle with radius 1, so its area is pi times 1. Pi r squared. So my answer here would be pi. If I wanted to solve that integral, it would be a pain to set up. Because if you set it up in Cartesian coordinates, you can't evaluate the second integral. You'll have weird squares in it, and the polar is hard to set up. So I'm not even going to try that. Just if you got to the point of trying to set up something like this and had no other information, you might wonder, maybe I actually didn't need to set up that integral. Or you could set it up and not finish evaluating it in Cartesian coordinates if you wanted to. Just solve this thing. For your y. And then your x must be bound between 1 and 3. And then that would be about as far as you could get. I'll go ahead and write that down. So if somebody asked you to evaluate this and you forgot that area thing on an exam, you could at least get to that point, even though you couldn't finish it. Are there any questions about that? Okay, cool. Any other questions in general? Is the problem similar to problem 3 in the notes? This one that we're looking at? Oh, is there a problem similar to problem 3 in our notes? Triangle. Let me go check those. Yeah, so I'm gonna check real quick the notes to answer your question, and then we should at least talk about the orientation real quick. So yeah, you're gonna want to set this one up like the first example we did. It's actually a little bit easier a surface. And sorry, I don't have the filled in ones here. But sort of like, yeah, sorry, the closest we get is that first one, and you just want to sort of, there isn't a fancy plane to cut through it. Instead, you've got a flat shape that's intersecting the XY coordinates. I'm going to draw it and then also talk about the orientation. And then maybe that'll be clearer than me just pointing at half filled in notes. So your surface is x plus y plus z equals 1. Z equals 1 minus x minus y. So there's x, y, z, and C is the intersection of that plane and the 3 coordinate planes, x, y, and z equal to 0. So every time we've had a problem about this shape, it was when we were doing triple integrals and we integrated over this triangular wedge. So it's being cut off by y equals 0 there, and by x equals 0 there, and by z equals 0 there. But this plane would actually be like a flat sheet that cuts through everywhere if we weren't cutting it there. And the curve that we're integrating over here is the triangle where this gets cut off. So it's those 3 lines that I drew to start, like this. But I may have drawn those arrows in the wrong direction because I haven't paid attention to the orientation yet. Oh, that's going to be too hard to erase finally. I'm going to do the back button. So I'm not totally sure the direction it goes yet, but I do know that I'm trying to integrate over this thing. And so the corresponding surface is going to be the area that fills it in. That slanty part of this sheet, basically. The triangle that doesn't lay in any of the other coordinate planes. Does that make sense so far? Okay, cool. And then to apply Stokes' theorem, we're going to have to understand like what direction this curve is going. So we're told traverse clockwise when seen from below, which means if you're looking from here up at the triangle, like that way, it looks like it's clockwise, which is really hard to visualize. So just swap it. If you're looking at the triangle from here, like we are, coming out of the paper and looking into it, it's going to be the opposite. So it's clockwise when seen from below, so it's going to be counterclockwise when seen from above. So I just drew counterclockwise from the direction that we're looking at it, but if you could somehow get inside the screen and be looking from behind it, then it would look clockwise. So that's exactly what's happening to this curve. So the orientation is going to be this way. Reason we care about that is because it means that our normal vector is going to come out that way from the shape that I just drew. Do you have any questions there? Okay, so to do this problem, you're asked to evaluate this, but we're just going to go ahead and do this. And all the important parts are that we're going to have to calculate del cross F, which I trust that you can do. We're going to have to find the normal vector, and we did the hardest part so far, which is identifying the orientation. Now we could go ahead and do that minus fx minus fy1 for z equal 1 minus x minus y. The other thing we could do is we could say this was an equation of a plane. I know that the normal vector is the constants that are on all the x, y, z parts. That's the first thing I learned in this whole class. Either way, you will arrive at the conclusion that n is 1, 1, 1. And you would have to normalize by the magnitude. And then the only part that's left really is to figure out what ds is and what area you integrate over. And you do this the exact same way as we learned for surface area. So you're gonna say ds is you don't square that last part. ds is root fx squared root fy squared plus 1 dA. And the region of integration is the shadow of the surface in the xy plane. So you're going to set up like the double integral as the two outer bounds that you usually do when you're trying to integrate over this 3D surface. And then the only complicated part is that you have this extra factor in front of the dx dy to kind of convert to saying I'm actually integrating over the slanty surface up above. Do you have any questions about that? Okay. Did that answer? I guess, long story short, there isn't something super similar, but this is how you sort of bridge that difference. Did you have any other questions? Okay, cool. Then I'm going to go ahead and end this call and then get the video uploaded. If anything went too fast, you can go ahead and check it out. It should be ready in like 30 minutes.